Now we'll move on to finding the derivatives of inverse trig functions. Let's consider the graph of y equals sine x. If we find the inverse relationship of that, we do that by swapping x and y. But graphing that, you'll notice that this relationship isn't a function, but the function y equals sine inverse of x is a function. This is accomplished by restricting the range of the relation. All the inverse trig functions are restricted, as you can see on this diagram. Sine inverse, tan inverse, and cosecant inverse are restricted to quadrants 1 and 4. Cosecant inverse, secant inverse, and cotangent inverse are restricted to quadrants 1 and 2. We can use this when developing the formulas for inverses of inverse trig functions. So let's consider the function y equals sine inverse of x. We can take the sine of both sides and take a derivative implicitly and isolate for dy dx. But we'll notice on the last line we have 1 over cosine y. To substitute that out, we can use our second line and draw a right triangle. We can have y as our angle, and since sine is opposite over hypotenuse, we can label in x over 1 to give sine y equals x, and we can solve for the other side using Pythagorean theorem. Since sine is restricted to the first and fourth quadrant, this adjacent side has to be positive, so we're only taking the positive root. Now, using this triangle, we can substitute out cosine y for square root of 1 minus x squared. We can do this again for the function y equals secant inverse of 1 over x. Once again, we take the secant of both sides, take the derivative implicitly, isolate for that derivative, and use that second line to draw a right triangle with y as our angle and 1 over x, since secant is hypotenuse over adjacent, and we can solve for that opposite side using Pythagorean theorem once again. And since secant is restricted to the first and second quadrants, we'll only take the positive. Now we can sub the values in, secant y being 1 over x, and tangent y being everything that's under that root over x. And simplifying, we get that our derivative is negative 1 over 1 minus x squared. One last example, we can find the derivative of y equals cosecant inverse of x. So once again, we take the cosecant of both sides, take the derivative implicitly, isolate for dy dx, and draw a right triangle using the relation on the second line. Y is our angle, and 1 over x. But notice that since the hypotenuse of the triangle needs to be positive, we'll insert absolute values around the x. And since cosecant is restricted to the first and fourth quadrants, that bottom side has to be positive. Now we can substitute the appropriate values in for cosecant y and cotangent y using the triangle. You might be wondering how we justify the absolute values on the hypotenuse of the triangle. If we consider what happens when x is negative, we would actually have to draw a different triangle. Using that triangle, it's clear to see that you'd still get the same result for cosecant of y, but you would actually get the negative of the desired result for cotangent y. But since the absolute value negates x, by including the absolute value in our derivative, it accounts for that flip of sign for the cotangent y. So yes, inserting the absolute value is valid. So that's how you derive the derivatives of the inverse trig functions. But if they're given to you, they're easy to use as well. Let's consider the example y equals sine inverse of x squared plus 2x. So first we can make a substitution to make the equation look a bit nicer. Then, directly from the formula sheet, we can copy down the derivative and substitute back u equals x squared plus 2x, and u prime would be 2x plus 2. You could leave it here, but there's also more simplification that could be done. We could factor the bottom by difference of squares, and notice that the second factor is a perfect square. And one last example, if we consider the equation y equals cotangent inverse of sine of 2x, we can make a substitution to make things look nicer, and then copy the derivative from the formula sheet, and substitute back in u equals the sine of 2x, and u prime is equal to 2 cosine of 2x.